Here we are given the equation for the position of a particle. This sinusoidal behavior, basically the particle moves back and forth, and it's what's called a simple harmonic motion. We'll see this later on in the class where this comes from and how to deal with it. Here, as long as we're given it as its position as a function of time, we can find the average velocity, the instantaneous velocity, the average acceleration, and the instantaneous acceleration. When we have the average velocity of a particle, the average velocity of a particle is defined as the change in position over the change in time. We want to know where the particle was in one point in time, where the particle is later, and we find the average velocity, which is how fast it must have been traveling if it went directly from one point to another. We'll see with the instantaneous velocity that it doesn't necessarily have that perfect uniform motion. But if we want to find the change in time, the change in time will be t final minus t initial. And if we want the change in position, that will be the final position minus the initial position. In this case, we're talking about t initial being 0 seconds, t final is 2 seconds. So we can see immediately that delta t will be a difference of 2 seconds, 2 minus 0. But we're also interested in the positions. The final position is the position at 2 seconds, which is two centimeters times the sine of pi times 2 over 4. Here, pi times 2 over 4 is pi over 2. Sine of pi over 2 is equal to 1. And so our position is 1 times 2 centimeters, and thus is 2 centimeters. Our initial position will be 2 centimeters times sine of pi times 0 over 4, because t is equal to 0 in this case. When we plug in a 0, we get sine of 0. Sine of 0 is 0, and so the whole term is equal to 0 centimeters. Our average velocity then is 2 centimeters minus 0 centimeters over 2 seconds, and thus we will get an average velocity of 1 centimeter per second. We were told specifically that it was in terms of centimeters. We're not told anything about time, so we assume that time is done in units of seconds as our base unit. Here we're given the position of a particle as a function of time. The position is sinusoidal, meaning the object, which will move in the y direction, move vertically, will look something like that. And we'll see later that this is simple harmonic motion, that is the oscillation. And we'll see later on more detail about where that comes from. For right now, as long as we have the position as a function of time, we're able to find the average velocity, the instantaneous velocity, average acceleration, and instantaneous acceleration, just mathematically. If we are interested in the average velocity will be our change in position over change in time. If we're interested in the average velocity between t equals 0 and t equals 2 seconds, that will be the final position minus the initial position over the final time minus the initial time, or that will be the final position is the position at 2 seconds, the initial position is the position at 0 seconds, The final time is our 2 seconds. The initial time is our 0 seconds. Now, if we look at y of 2, we're plugging 2 into our equation here. We have 2 centimeters times the sine of pi times t equal 2 over 4. This term here is pi over 2, and sine of pi over 2 is 1. And so y of 2 is equal to 1 times 2 centimeters, or 2 centimeters. When we look at y of 0, we'll see sine of pi times 0 over 4. This whole term is going to be 0. Sine of 0 is 0. And so that term is 0. This means that our average velocity is 2 centimeters minus 0 centimeters divided by 2 seconds minus 0 seconds. And we'll see that that ends up being 1 centimeter per second. We were told specifically that the position is measured in centimeters. We're not told anything about t, so we will assume that t is in seconds. We wish to now find the instantaneous velocity at several points in time. The instantaneous velocity, or just the velocity, is found by taking the time derivative of the position. This is the velocity. You can also write it as the velocity in the y direction if you so choose. To take the derivative of our position function, the 2 centimeters is a constant. That's out front, so that won't change. In this situation, when we take the derivative of sine, we get cosine. Whatever was inside of the cosine stays there. And then we must multiply by the derivative of what is inside the function to follow the chain rule. So we can simplify this. We see we have pi over 2 centimeters times cosine of pi t over 4. If we want the instantaneous velocity at t equals 0, here we have a 0 term. Cosine of 0 is equal to 1. So our answer is 1 times pi over 2 centimeters, and that gives us pi over 2 centimeters, which is approximately 1.57 centimeters. We could do the same thing for the position at 1 second. We still have pi over 2 centimeters times cosine of pi times 1 over 4. This term here is going to be pi over 4. The cosine of pi over 4 is the square root of 2 over 2. Our solution then is going to be pi root 2 over 4 centimeters. This is the actual correct amount that you should keep. However, when you get a strange number here where you have an irrational number like pi, you have another irrational number like root 2, it is best to approximate it. And the approximate value there is about 0.56 centimeters. We can also find the average acceleration of the particle. The average acceleration is the change in velocity over the change in time. So in this case, we need to know what the velocity is at 2 seconds and what the velocity is at 0 seconds. divided by the time. We found before that the velocity as a function of time is pi over 2 centimeters times cosine of pi t over 4. We found that v of 0 is pi over 2 centimeters, which is approximately 1.57 centimeters. If we wish to know what the velocity at 2 seconds is, if we plug in 2 seconds here, we get pi over 2. Cosine of pi over 2 is 0. And so our velocity will be 0 centimeters per second. To find the average acceleration, then, we have 0 velocity minus pi over 2 centimeters per second. We're dividing by 2 seconds minus 0 seconds is our time interval. And that gives us minus pi over 4 centimeters per second squared. This, again, is the exact amount. But we can approximate it as negative 0.79 centimeters per second squared. What this is telling us is that we were going to the right. A few seconds later, we're motionless, so our average acceleration is negative. We must have been decelerating or slowing down in order to end up stopping by time equals 2 seconds. But here, to find average acceleration, we find it from looking at the velocity at certain points in time, divided by the time interval. The final step is to find the instantaneous acceleration. We said that the acceleration is the second derivative of the position, and that's the position function that we're given. So if the position, and I should keep my, since we're talking about vertical motion, it doesn't really matter what we call our axes, but it makes more sense to try to be consistent. We're given our position function, we take a first derivative, which gives us our velocity. We said that comes out to be pi over 2 centimeters times cosine of pi t over 4. Because we have the 2 centimeters times a factor of pi over 4 that we get from the chain rule is tied into the constant, the sine became a cosine when we took the derivative. When we take a second derivative, which is the derivative of the velocity to find the acceleration, what we get there is pi over 2 times the derivative of cosine here is negative sine, and whatever's inside stays that way for the time being. But then we have to multiply by the derivative of whatever's inside to satisfy the chain rule. So we can rewrite this to find So we found the acceleration as a function of time by taking multiple derivatives of the position function as a function of time. So now if we want the acceleration at 0, when we plug in 0 for t, we get sine of 0, which is 0. When we want the acceleration at 1, we get our constant factor times a sine of pi times 1 over 4. this pi over 4 is 45 degrees. Sine of 45 degrees is a factor of root 2 over 2. And so we can simplify, we can find the total value as and we can approximate that value as 0.87 centimeters per second squared.